Hello, welcome back to Waves and Whatnot. Today we're going to start the next kind of chunk of our unit, very related to what we've been covering before on waves in general. We're going to focus in on sound waves for a little bit, so we're dealing with definitely everyday life things. So what is sound? Okay, I think we probably mentioned before that it's a wave. What kind of a wave is it? Okay, so this represents a speaker that is moving back and forth. What kind of wave? What kind of wave is this? That is not a transverse wave. It is a longitudinal wave, or a compression wave, or pressure wave. Any of those kind of mean the same thing. So, what do these dots do you think represent in my little wave simulation? They represent particles of air or air molecules, and when the speaker drives forward, it creates a compression where the air molecules are closer together than the average distance, and then when the speaker drives back, it creates this rarefaction. Where the air molecules are a little more spread out. So anyway, it is a longitudinal wave. So what is making the sound? The speaker here. What is the speaker doing that creates sound? The same thing that my vocal cords or your speakers are doing right now on your computer or earbuds. They are vibrating. That's all you have to do to create sound is vibrate something, and then you got it. So, how do your ears pick up that sound? Well, your ears are. I used to have an animation showing this, but it's no longer. So your ears would be represented by another diaphragm or a type of membrane over here. And when the compression reaches your eardrum, it'll drive it back. And then when the rarefaction meets your eardrum, it'll vibrate forward. So it'll just basically oscillate back and forth at the same frequency of the waves, and that's how we pick up sound. And your body turns that vibration into an electrical signal for your brain. So pretty cool. What makes a sound loud? Okay. This is a soft sound, and this is a loud sound. What is the difference between these? Well, the loud sound has a higher amplitude. So the speakers, or in this case the vibrating tongues of the fork, are vibrating with a greater amplitude or wider. Okay. What's the difference between a high pitched and a low pitched sound? Well, all the difference between them is frequency. A high frequency sound like this wave over here, which has a short wavelength, would be a high pitched sound. Okay, whereas the low frequency, longer wavelength would be a lower pitch. Okay. Normally, this is when I would take a tuning fork and I would strike it and dip it in a cup of water, and you would see all the water splash out of the cup. By the way, if you come in person, feel free to ask me to do these demos, because I may just forget. But anyway, the water splashes out because of the vibrating tongs of the eardrum. This is normally when I would hook a speaker up to a frequency generator, which can generate any frequency that I want to generate. So typically I would start it at 1 or 2 hertz, and you could connect it to a speaker, and you could see the speaker vibrate back and forth very slowly, and you couldn't hear anything. And then as I get around 20 hertz, you'll start to hear a low pitch sound. Then as I keep going up, the pitches gets higher and higher. And then once we reach about 20,000 hertz, that's when you guys drop out. Lower for you kids that blare your earbuds too loud, because you do permanent damage and you lose your higher pitch, higher frequency hearing first. So That's because the average hearing range is 20 to 20,000 hertz. But as you age or as you damage your hearing, you tend to lose this higher frequency hearing first. Had a boss of mine who had his cell phone ringing in his pocket and just kept talking like nothing was going on. And I told him his cell phone was going off, and he said, "Oh yeah, I can't hear that," because he was in the artillery in the military and damaged his hearing. So he lost a lot of hearing. So when you strike something like a guitar string, most of the vibrations that are going to occur in that string are in the first harmonic standing waves. That's how a certain string gets its pitch. You can do certain things to change that. We'll cover that in a little bit. So what's the frequency of the first harmonic? So this is the bridge of a guitar, if you bear with me. All right. So the wavelength of the guitar, or of the first, I'll try that again. The wavelength of the first harmonic is equal to 2 times the total length between the ends of the string. Okay. Now we know that V equals lambda F, so we'll combine that with our fundamental harmonic relationship here, and solve this for frequency, and we'll get that frequency is equal to the velocity that the waves travel down the string divided by 2 times the length between the ends of the string. Okay, so we see there's 2 ways that you can change the frequency of the fundamental harmonic of something like a guitar string and change its pitch. You can change the velocity, or you can change the length. All right. So what happens to the velocity of the guitar string as it gets tensioned? Because every string on the guitar has a separate tensioner on it. So what happens to the velocity as you tighten that up? Well, the waves are gonna travel faster down that string, the tighter that tension is. So what's that going to do to the frequency of the vibration and the frequency of the sound you hear? If you make this bigger over here, okay, that's going to increase the frequency, and you're going to hear a higher pitch. So that's how you tune a string, is by increasing and decreasing the tension, changing the wave velocity, and getting it so that it's in tune. All right. So remember now, if you remember, there's 6 different strings on a guitar, from what I gather, there's one that's very lightweight. Okay, the nylon or catgut or whatever it is, I don't really know. The other thing you can do is alter what the string is made of. So as you get to the left side here, you got these strings that are metal wrapped to increase their mass. So as you increase the mass per unit length, you decrease the wave velocity. Okay, and going back to our previous relationship, if you decrease the wave velocity, you decrease the frequency. So these heavier strings are lower pitched. Okay. Now, you don't have to just tension the guitar string, change its tension to change the sound you get from it. You can get a whole lot of different pitches from one guitar string without touching the tensioning knob. Okay, and that's because you can change the other thing. So instead of changing the velocity, we can change the length. And how do you do that on a guitar? How do you change the length of that string? Put your finger down. Okay. So that wave effectively becomes shorter, and as I decrease the length, okay, I'm going to increase the frequency. So the closer I bring my finger down to the other end, the higher frequency I'm going to get. Okay, a little review from before. How will the following affect the speed of sound? Making a sound louder. Which travels faster? Loud sound or a soft sound? Okay, neither. Amplitude doesn't affect the velocity of a wave. going from a low note to a high note, which is faster, a low note or a high note, traveling from one end of the wall to the other? Neither. Okay. Frequency does not affect the velocity of a wave. Going from air into water. Okay. What happens to the speed of a wave as you change materials? Well, that does change it. Okay. The only thing that affects the speed of a wave is the medium. And when you change medium from air to water, the wave is going to get quite a bit faster. Okay. So just like waves in water can cancel, and waves on a string can cancel, and waves in a standing wave can cancel, and all waves can cancel, I can cancel out sound waves. Okay. I can send sound from two different sources, two different locations, and you can have constructive and destructive interference. So this represents a wave source, and here I've got the concentric waves that are traveling out in all directions. Here I've got a second small one. I've got a separate set of these, okay, representing two waves that are being generated. And what you see is along this line I've got constructive interference, and that's because the waves will be adding up and the sound should be louder. And over here in this region I've got destructive interference, and the sound waves will cancel and it'll get quieter. So yeah, remind me to do this. Because this really is a pretty cool demo, where you can walk around the room and the sound gets loud and soft and loud and soft. It's one of those things that you just kind of have to like hear to experience. So if I send two sound waves and they're in phase, okay, the result is constructive interference, just like with regular waves. Now that's not what a constructive interference in a compression wave or a longitudinal wave looks like. Okay, here I've got a compression and that overlaps with another compression, and what I get is a really compressed compression, okay, and a really rarefied rarefaction. Okay, that's what it looks like. Here I've got a crest and a trough, okay, and those line up like that. So I'm out of phase, and I get destructive interference. This is what that would look like with sound waves or any transverse wave. So here I've got a compression, and that lines up with a rarefaction. And what you see when I add those together is they all just cancel out, and I get even air pressure all the way through. Okay. So what I'm going to do is place two speakers, and there's going to be regions where those line up and you get constructive interference, and destructive interference where they are out of phase. So I'll do that for you if you remind me. Okay. Now if you play different frequencies of sound from two different speakers that are very close but not identical in frequencies, you get something different. It's called beats. Okay. And so which of these is the higher frequency wave? It's this wave, because the waves are shorter. So what you're going to get is when these things add up, okay, sometimes you're going to get constructive interference, and other times you're going to get destructive interference. So it'll just be kind of a mix of that. So as the waves are moving towards you, you're going to get constructive interference, loud, destructive interference, quiet. So you're going to hear this loud, quiet, loud, quiet, loud, quiet, loud, quiet. It's because they line up because the frequencies generate slightly different wavelengths. So here, just to kind of see the effect with the combs, these combs are just slightly different spaced, okay, and I'll put them overlapped. And here we've got constructive interference, and here we've got destructive interference. And then as this travels forward towards you, we're starting out with constructive interference. I thought I had it move. There I do. Okay, so when you add those, you get this regular up and down. So here we've got destructive interference. This is the sum of the two waves. And here we've got constructive interference and then destructive interference. How quickly the effect of the beats are heard depends on how close together the sound frequencies are. Okay. If they're pretty close, you get this low frequency beat. Okay, it's I probably should not do sound effects. But as you get bigger and bigger difference, okay, these wave pulses, these beats get more and more high frequency. If you want to hear beats, you can hear beats on just by playing with an app. Google, let's see, Google Sound Beats Applet. Sound Beats Applet. Oh, I can actually probably just do it. Okay. And click on O Physics here. And this is kind of showing you what you get when you add these waves. So here we're going to I'm going to play a 500 hertz frequency and a 502 hertz frequency. So you can hear that modulation of the sound. And then I'm going to play a 505 hertz and one. Now, as we get further apart, you'll notice the speed at which those beats come at you gets faster. So the higher the difference in frequency, the greater the frequency of the beats. Really, to figure out the frequency of the beats, you just subtract these. So you're going to hear a 5 hertz beats because 505 minus 500. Yeah, I don't know if you can hear that, but so that's 5 times per second. And then as you get to be too big of a difference, it gets to be hard to hear. So it just sounds like 2 frequencies. You can't really. Okay. So the frequency of the beats is basically just the difference between the frequencies that are being played. So nothing complicated there. All right. Okay. So sound can resonate like a string between boundaries in a standing wave. So you can create a standing wave with sound, and what you get is that really exaggerated constructive and destructive interference. The effect is a greatly increased amplitude, and if it's a bigger amplitude, then we know it means sound, or it means loudness. So the trick is that when you send a wave, it has to reflect back and be in phase with itself. Okay, so if we start and end with a node, okay, then it's going to reflect back and start and end with the node, and it'll be in phase. Okay, so here I've got a single wave that I'm sent. Okay, and then once it goes through, okay, this is going to look like this. Okay, because remember, and then it's going to. So anyway, the reflection is going to be in phase with the wave, the incident waves that are still coming down. So if we can do this also with an open pipe, so a pipe that's open at both ends, so when I send a wave down, it's actually going to reflect back, even though it's open. It'll actually reflect back into the tube, which is strange to me. Seemed like it would only reflect if it was closed, but there is a little bit of an explanation for that. That makes sense. So, and here it is. So here we've got a uniform air and an open pipe. Okay. So I'm going to create a low pressure region here, a rarefaction, and then the air molecules are going to rush to fill that in. They'll do that from both sides, but they'll rush from this side too. And then as that happens, the rarefaction will just keep moving to the right. Okay. Now when it reaches the other end, okay, what's going to happen is that so this is open to the room now. The air molecules from the room are going to rush in to take place of the void of air, okay, trying to equalize pressure, and really, truth be told, the pressure stays equal at the ends of the pipe, but this is just for an analogy, okay. So now, when all that air rushes in to fill that void, it actually creates a high pressure pulse or a compression. Okay, and then that compression will travel, okay, and then the compression will reach the other end, and then it'll be converted to a rarefaction. So I'm having a brain fart here. So the waves are inverted when they're reflected, just like on a string. Okay, when a string meets a rigid boundary, they are inverted. Okay. So basically, open pipes obey the same rules as waves on a string that we've been doing. So the key thing here, in order for this to work out, is to have your frequency and your pipe line up so that you start and end with a node. Okay. So if you've got a certain frequency, okay, you can have multiple waves that will do that. If you have a certain length of pipe, you'll have multiple frequencies that'll do that. That's a key thing. So if the length of the pipe is equal to half the wavelength, this is going to be your first harmonic, your fundamental harmonic. The next time the waves I start and end with the node is when I reach the next hump, and I add another half a wavelength, and I have just the L equals lambda, okay, and then for my third harmonic, we have L equals 3/2 lambda, okay. So here's the simple relationship between the length of the pipe, and this is only for open pipes. You've got it's different for closed pipes. So using that rule, L equals n lambda over 2. This is organized the other way, so this is equal to L equals over lambda 2. So basically, this is just to show you that for a certain wavelength of pipe, okay, that's set, or for a certain length of pipe that's set, this is the relationship between these. Okay, so here I have half a wave, here I have a whole wave. Okay, here I've got 3/2 of a wave in, and here I've got 4/2, so 2 waves in. Okay. I'm not sure where I'm going. I think we've already said this. Okay, this is a good question though. Is the first harmonic, is this the lowest pitch or the highest pitch frequency that will resonate in a given length of pipe? Okay. Well, it's the longest wavelength. Okay, and therefore long wavelengths are low frequencies. So the fundamental harmonic is the lowest frequency wave that will resonate in a length of pipe. Okay, and normally I would whirl around my flugels, but you're not there. Okay, so let's say I took my my pipe and I chopped it. Okay, what's going to happen to the frequency of the first harmonic? What's going to happen to the frequency of the first harmonic? Well, the wavelength is going to go down, which means the frequency has got to go up. Okay, so keep that in mind. Okay, I'm not going to make a big deal out of this. There won't be a test question along these lines, but let me just throw this out here. So a displacement node, meaning where the air molecules move the most, okay, is a pressure antinode. Okay, so I'm sorry, displacement node is where they move the least. If I didn't say that properly. So a displacement node where they move the least is a pressure antinode. So open ends are pressure nodes. Okay, they're constant pressure because they stay lined up with air pressure, the room pressure. But they're displacement antinodes, and that's because the air can move back and forth the most because they're open. Closed ends are pressure antinodes, so they have the biggest change in pressure. Okay, but they are displacement nodes, which means the air can't move back and forth there at all because they're stuck in place. So this just kind of shows a closed end and an open end. So here our open end. I guess we look at our closed end first. So this is a displacement node. Nodes mean no change because the air molecules aren't moving, vibrating back and forth as opposed to this other end. And they're pressure antinodes. Okay, you see they get the biggest change in pressure, the biggest change in spacing of the atoms. Whereas over here the atoms stay pretty much the same distance apart. Okay, here they get closer. It's easier to see actually over here. I don't know why it's a faultiness of the applet, but okay. On the other side, an open end. This is a displacement antinode. This is where the air is moving the greatest left and right, as over here. That's a node. Okay, and it is a pressure node. Okay, because the pressure is remaining to be remaining air pressure. So this shows the first harmonic of open-ended pipes. So you've got the greatest displacement at the ends. Okay. So anyway, all right, that's where we're going to stop. Sorry for the 27 minutes, but that's what we got today.